to help us analyze and understand the content of a signal, there's three properties that we can ask whether any signal has. We can ask whether it is an even signal, an odd signal, and a periodic signal. These are three key properties. There are many more, but the reason we're interested in these is because whether a signal has these properties will allow us to use certain analysis techniques. And if a signal does not have these properties, we might do some transformations, which we will talk about in this video, to get the signal into this form. So let's define them, and then we will do some examples. First of all, an even signal means that if you flip it about along the time axis, you get the same signal back. So if I write this in mathematical terms, x of t is the same as x of negative t. That's the time flipping transformation that we had from last time. So if I have a signal that I reverse the time axis and get back to the same signal, we see that it is an even signal. A common example would be a cosine, also a rectangular pulse centered at 0. So cosine, see if we reverse along the time axis, we're going to get back to the same signal, and the same for a rectangular pulse if it has the same extent in both directions. So a even signal might go on forever, like a cosine. It might gradually die out, such as a damped cosine, which is damped the same way in positive and negative time, if it decays the same way on both sides of the time axis, or it might abruptly cut off, like the rectangular signal. So an odd signal tells us that when we reverse the time axis, we don't quite get the original signal, but we get the negative of it. So a common example here would be a sine wave. Okay, so for example, if I have x of t, and this is a sine wave with no phase shift. So if I say x of t is 3 sine of 4t, and then I want to know, given that signal, is it even, odd, or neither? That's a possibility also, that a signal might be neither even nor odd. I substitute in negative t, and in the case of the sine function, we know if we put in the negative angle, I get the negative of the value than if I had the positive angle. So negative. And this here is negative x of t. Therefore, we say that is an odd signal. So it's even signals and odd signals, such as sines and cosines, as you know from circuits, make it easier to analyze a signal. If we can avoid dealing with phase shifts in the argument of a sine or a cosine, that simplifies certain analyses. So that's a motivation for wanting to learn this important fact now, that you may already know, that any signal can be written as a sum of an even signal and an odd signal. Now, the reason we do this is because even and odd signals are going to be easier to analyze in a lot with a lot of the tools that we're going to learn later in the class and that signal processing engineers use. And it's really a powerful fact that if I have any given signal, any arbitrary signal that we measure, since it can be written as a sum of these simpler types of signals, that's going to help us with analysis. This is related to the concept of superposition, where in a circuit you could consider two sources separately and figure out what their impact on an output waveform is, and then add them back up. So that's we're going to do here. Now, I'm going to state the formula for a signal that is derived from X and it is even. And I'm not going to do a full proof. We don't need that. But we're going to state this formula for the even part, and then we'll derive the other and show that the even and the odd part that we can calculate for any signal will in fact be even and odd, and when added together will give us that original signal. So here's what we do. We're going to have a fraction, and we take x of t and we add it to the time reversed version of x of t. So that is going to make an even signal. Let's confirm that it's even. So we take x e of negative t, and we see whether we get back to the same signal. So I change all the t's to negative t's. So I have x of negative t plus x of negative t, which is x of positive t, of course. So here I have x of t, because I've taken the negative twice, added to x of negative t, divide by 2. So that's the same that I had in the original definition. This negative and negative matches up to this positive, and this negative matches up to that negative. So I can say x e of t, just given this definition of x e of t, we can see that it's x of negative e of negative t is equal to x e of t. Therefore, x e of t is an even signal. Okay, so now let's calculate what the odd part will be and confirm that it's odd. So building off this idea that we're decomposing the signal into two parts here, the remaining part, x odd of t, is going to be the whole signal minus this, what we've just defined x e of t to be. And we'll substitute in. Okay, and now we can consider this term on the left to be 2x of t over 2. And I have 2x of t's in the numerator minus an x of t. So I have x of t left over in the numerator, and then I am subtracting the x of negative t in the numerator. And I divide that by 2. And now we're going to confirm that this is odd. And if we can confirm that it's odd, then we have correctly derived a method of taking any arbitrary signal x of t and breaking it down into an even part and an odd part. So we use the definition. We say, well, let's take x odd and evaluate it at negative t. If it's an odd signal, we're going to get the negative of x odd at positive t. So let's see if that happens. So I take my final equation above for xo of t, and I substitute in negative t. So I'm taking this expression here, and I'm substituting in for all the t's negative t. So I have x of negative t minus x of negative t over 2. And I have then if I simplify that a bit, I have x of negative t minus x of t over 2. And now we see the numerator here is x of negative t minus x of t. That's the negative of this here. I've switched the two terms being subtracted, so I have the negative. So that's the negative of this value, which means it's the negative of this equivalent value here. So what I end up with is negative x of odd of t, and therefore I have confirmed that xo of t is an odd function. What we're going to do in a second to finish off this video for waveform properties is we're going to talk about the third property. Then there are two additional videos that follow this one that do detailed examples with specific functions showing how you can break them down into even and odd parts. So those are additional follow-on videos for this one. Let's go on to talk about the final important waveform property in section 1.3, and that is whether a signal is periodic. And we're also going to have the concept here of fundamental period. The reason, again, that we're considering all these properties, even, odd, and periodic, is because if a signal has these properties, it will lead us to certain analysis tools that we're going to develop earlier in the class. Now, if a signal is not periodic, which most real-world signals are not periodic, there will be different tools that we use, but we're going to start with the periodic case because it does allow us to use a certain class of very powerful analysis tools to understand signals and systems. So we say a function x of t is periodic if I can shift it by a integer multiple of a certain amount and get back to the same value. So if t0 is the smallest number that satisfies this relation, that if t0 is the smallest non-zero number that satisfies this, we call it the fundamental period. So if t0 is greater than 0, so we're going to have positive periods here, and it's the smallest such that this is true, then we say t0 is a fundamental period. Okay, so as an example, if we have x of t is 5 cosine 3t plus 5, well, we have here our frequency is going to be 3 radians per second, which is 2 pi times the frequency in hertz. So our frequency in hertz is 3 over 2 pi. Okay, so then associated with that, we would have a period, which we call capital T, and reciprocal hertz, so we have seconds. So we have 2 pi over 3, so that's about a little over 4. That would be the duration to repeat the signal. So that's the smallest number that this cosine is going to repeat in. So here, this is going to be, in this particular case, 2 pi over 3 seconds. But we could also say the period is any multiple of this smallest number that the signal repeats in. So the period, we could say, is 2 pi over 3, or twice that, 2 times 2 pi over 3, or 3 times 2 pi over 3, 4 times 2 pi over 3. So any of these values, are considered the period of the signal. But the rule is, the fundamental is the smallest one that is not 0. So saying 0 is the period, then that if I put 0 in here, n is 0 or t0 is 0, that makes it true, but it's not a very interesting statement. It just says x of t equals x of t. But this periodicity property, to say a signal is periodic, is going to allow us to use a certain analysis tool called a Fourier series and some other tools later in the class that will help us analyze signals. So that is the end of this video. The next 2 videos are going to go back and give some examples of even and odd signals and how to decompose any signal into even and odd components.